Hey everyone, in this video we're going to do a little bit more with planes. Be a shorter lesson than last time. Do a few examples and I'm going to show you guys how to find the angle between two planes. So let's get started. So as I said, we're just going to do a few examples, not a ton of new stuff in this lesson. So you can almost treat this as a bit of a warm-up, and at any time, if you just want to pause the video and just do the problems yourself, and then unpause to check, that's fine. You don't have to watch everything. So let's find the scalar equation of the plane through 2, minus 1, 0, with a normal of 1, 2, 4. So in our last lesson, we talked about this scalar or Cartesian equation of a plane, ax plus by plus cz plus d equals 0. And we talked about how A, B, and C are a normal to the plane. So right away, we can pop in those guys. X plus 2y minus 4z plus d equals 0. And one way to find d is just to plug in a point you have. X equals 2, y is minus 1, z is 0, so it's gone, plus d equals 0. That gives you 2 minus 2, and so you actually get d equals 0. And so the equation for this plane is just x plus 2y minus 4z equals 0. That's it, the scalar equation to that plane. So just a quick example, a warm-up almost, that we did a problem. We did a couple problems like that yesterday. So hopefully you did well on that one. Okay, this is kind of a new kind of problem. So we talked about in our last lesson different kind of ways that planes can be described. We saw that 3 points make a plane. We also talked about how a line and a point that's not on that line can make a plane too. We're going to find the equation of the plane in this question given a point and a line. So if you recall, there are 3 things we need for to define, or at least a vector equation, right? We need a point and 2 direction vectors. And to get the scalar equation, we needed a normal. And 2 direction vectors could help us get that normal with the cross product. So really our big question here right now is, how can I find 2 direction vectors so that I can do the cross product and get my normal? So if you want to think about that, you can, and pause the video and think, and unpause when you're ready. But the solution is, well, we're given 1 direction vector already, and that's the direction vector of the line. That will also be a direction vector for the plane. So 3 minus 1, 0 is 1 direction vector. And our second direction vector can come using the 2 points we have. We have that 1, 2, 3 is in the plane, but also 2, 2, 2 is in the plane. And so maybe I'll just call that Q. And so a second direction vector could be the vector PQ. So 2 minus 1 is 1. 2 minus 2 is 0. 2 minus 3 is negative 1. So just subtracting the components there. So now that we have 2 direction vectors, we can find the cross product between them. Normal would be A cross B. Let's just set up our little visual for that. Negative 1, 0, 3, negative 1, and then B, 0, negative 1, 1, 0. So what do we have? We have for x, we have 1, take away 0, so that's 1. We'll have 0, take away negative 3, that's 3. And we'll have 0, take away negative 1, that's 1. So 1, 3, 1. And so we've used 2 direction vectors to get a normal. And now it's just like the previous question. We have our normal. So we know our scalar equation is going to look like x plus 3y plus z, 1, 3, 1, plus d equals 0. And then you can plug in any point you want, either 1, 2, 3, or 2, 2, 2. They're both points in the plane. I'll plug in 1, 2, 3. Z equals 3 plus d equals 0. That is 10 plus d equals 0. So d is negative 10. So the scalar equation for this line, x plus 3y plus z minus 10 equals 0. We got it. Right, so again, to get the Cartesian equation, you need the normal, and if you have two direction vectors, you can do that with the cross product. The key to this question was one direction vector from the line itself and a second direction vector from the fact we had 2 points on the plane. So let's move on. So I showed you guys an example of going from the scalar equation to the parametric equations. We did that by choosing very convenient parametric equations for two of the x, y, or z. Can you see a good strategy for this one? Here it's x plus 3y minus 3z plus 4. In this one, there's a strategy that really stands out because it's just x all by itself. So if you want to pause, maybe even look at that example from last time, unpause when you're ready. But because the x is isolated there, it actually would make more sense for us to have two parametric equations. Let's let y equal s, and let's let z equal to t. And let's make that two of our parametric equations. Because then x, the Cartesian equation becomes x plus 3s minus 3t plus 4 equals 0. And rearranging that, we get a parametric equation for x, negative 4 minus 3s plus 3t. And combine that with y equals s, z equals t. I'm going to show you guys. So this is our answer. And actually, that's the parametric equations. That's fine. I'd stop there. But I do like to expand it out, at least for a little while, just to show you guys what we actually have here. The second parametric equation is like 0 plus 1s plus 0t. And the third equation is like 0 plus 0s plus 1t. And so you can see by choosing our first two parametric equations like we did, basically we're saying, okay, our point is going to be the point where the y and z values are 0, and we get the point negative 4, 0, 0 is that particular point on the plane. And we set our direction vector, our first one, will have a y and z of 1 and 0 respectively. And our second direction vector will have y and z value of 0 and 1. And then we only had to solve for what the very first value was. And so we did that, and our vector equation would then be negative 4, 0, 0 plus s times negative 3, 1, 0 plus t times 3, 0, 1. And we've got it. Right. So, hopefully you got all three of those just on your own. We were equipped to do those after our last lesson. The last thing we'll do today, I think it's the last thing. We have one or two more things. Yeah, the last kind of, we'll do, I'll do an example with you and then have you try one. It's how to find the angle between two planes. So if you think about it, it does make sense for, two planes to, line up and form an angle, as in the diagram, this angle theta is here. But how do we find the angle between them? Well, it turns out the angle between two planes is the same as the angle between their normals. So now, intersecting lines will always have two angles. One will be, unless they are perpendicular, one will be acute and one will be obtuse. So we've said here, determine the angle between the two planes. Let's find the acute angle, just to be specific and leave no doubt. So our first normal, reading it from the scalar equation, is 2 minus 3, 5. And our second normal is 3, negative 1, 2. And if you recall, we know how to find angles between two vectors. It involved the dot product in the following way. You take the dot product of the two vectors and you divide by the product of their magnitudes. And those are all things that we can do. So dot product, let's go. 2 times 3 is 6. Negative 3 times negative 1 is positive 3. 5 times 2 is 10 on the top. On the bottom, the size of the first normal would be 2 squared plus negative 3 squared plus 5 squared. And the second magnitude, 3 squared plus negative 1 squared plus 2 squared. And I mean, you guys can work it out from here. You don't need me. This is just calculations at this point, but you can still follow along. So we get 19 over the root of, that's 4 plus 9, that's 13, plus 25, 38, and the root of 9, 10, 14. I'm just going to get a decimal value there. So notice that everything here is positive, which means this is going to spit out the, our calculators will spit out the acute angle, which is good. So I got 0.8238. And so the angle between our two planes, make sure we're in degree mode here, about 34.5 degrees. So really nothing new. You guys already knew how to find the angle between two vectors, but now you have that tool. If you're looking for the angle between planes, you find the angle between their normals, which isn't too hard to do, especially if you have the Cartesian equations, you can read them right off. So not too heavy. So let's do a similar problem. This one, there's a bit of a twist though, because here we don't know what the normal of these two, what the normals for these two planes are. So as a little before step, you guys have to find the normal for each plane. So I would suggest maybe pausing the video and thinking about how you can kind of pull out a normal from each of those two planes, and then it becomes a question just like before. But again, you have to think how can we get a normal for each one? So if you want to pause the video and go through that, I would really encourage it, and unpause when you're ready. Or you can follow along with me. So here's for pi 1. Remember, if we have two direction vectors, we can find a normal using the cross product. So our first normal will be 1, 2, 3 crossed with -1, 0, -5. I'll do my work down here. So 2, well, at least set up my visual. 2, 3, 1, 2, 0, -5, -1, 0, and I'll tuck in my normal right here. So what is that? -10, -3 subtract -5, so 2, and 0 subtract -2, 2. So -10, 2, 2. I'm going to make that, reduce that. I'm going to make that -5, 1, 1. Remember, if -10, 2, 2 is a normal, then so is -5, 1, 1. Those are scalar multiples. They'll both be perpendicular to our plane. Let's do pi 2 now. What are our two direction vectors? Well, we can pull them from the parametric equations, because this is the vector equation 2, 3, 0, no constant in the last one, plus s times -1, 1, 2, plus t times 0, -1, 3. And so our second normal will be -1, 1, 2 crossed with 0, -1, 3. And I'll set this up down below. 1, 2, -1, 1. -1, 3, 0, -1. We're good to go. So that's 3. Take away -2, so 5. And 0, take away -3, that's 3. And 1 take away 0 is 1. Is that what we get? Just double checking here. Yeah, so -1, 1, 2, and 0, -1, 3. Yep, that seems good. 1, 2, -1, 1, -1, 3, 0, -1, 3, 5. Yeah, looks okay. And now we're just in a spot like last time. So we can finish it off. So I might go a bit quicker than the last one, because we've already done an example like this. So N1 dotted with N2. So that'll be -50. Oh, wait, we're going to be using the smaller one. That'll be good, because that'll make the mental math for me easier. Back to my pen here. All right, so what do we get? We get -5 times 5, that's -25. Plus 3 plus 1. on the bottom. I mean, you guys should do it and show as much work as you need to. 25 plus 1, that'll be root 27. And the next one will be root 35. Get that as a decimal. So that would be 21 divided by the root of 27 divided by the root of 35. So a negative 0.6831. And so your calculator will spit out an an obtuse angle here. Second cosine, negative 0.6831. 133 degrees, 133.1, but we'll leave it as 133. So that's the obtuse angle between the planes. Doesn't really say determine the obtuse or the acute angle. So we can say, if the obtuse angle is 133, then the other angle has to be the difference between that and 180, so 47. All right, so you guys at this point need to be comfortable finding the equation of a plane, whether it's Cartesian, vector, or parametric, in a variety of situations, maybe given all 3 points like our previous lesson, maybe with a point and a normal, maybe with a point and a line, or 2 lines. And you should also be able to, given the Cartesian equation, find the other 2 forms. And now you also know how to find the angle between 2 normals. So here's a bit of practice for you guys to work on. We are almost done the course. We just have 3 more topics to do. We have to investigate, we know how lines in 2 space interact. You guys spent a lot of time in your grade 10 course doing that, and solving linear systems. So now we need to discuss a couple things, or 3 things. How do 2 lines interact in 3 space? What are the possibilities? How can 2 planes interact, and how can 3 planes interact? So 3 more lessons to go. We're almost there, guys. Hope you have a great day. Stay well. We'll see you guys soon.